We spoke briefly in class today about taking a vector, let's say V, looking at its size, and another vector, a matrix A acting on V, and looking at its size. Is there some relationship between this and this? Now this is a very complex matter. I just alluded to it in class briefly today, but it's not so easy. So let me give you an example. We took a matrix 1, 2, 3, 4 and asked you to act upon some other vector. Let's say the vector was something like, say, 3, 5. Now, by the way, one confusion that arose in class today was if I take this vector 3, 5, it represents this point going 3 over here and 5 over here. This is 3, 5. Of course, I could write this vector as 3, 5, write it as one row into two columns, or I could write it as 3, 5. That's my choice of notation. Here there are two rows and one columns. If I want a matrix like this, which is the 2 by 2 vector, to act upon this vector, it will act upon this but not act upon this according to the rows of matrix multiplication. So if I use matrix multiplication to act, I must write this like this. Okay, that's just a matter of notation. But that's a very complicated matrix. Let me give you a simpler matrix. Let me give you a matrix 3, 0, 0, 5, and let it act upon the matrix 1, 2. Now where does this send it? It sends it to 3, 10. Now what's the size of these matrices, of these vectors? This vector has got size square root of 1 squared plus 2 squared is equal to square root of 5. This matrix has got size square root of 3 squared plus 10 squared equal to square root of 109. There really is no relationship between this, and this that's meant to be obvious. However, this matrix is a very special matrix. This particular matrix is a very special matrix. It is called a diagonal matrix, and you can see why that is, because this matrix only has elements along its diagonal. Now, the thing about a diagonal matrix is it's very easy to find its action, because all you have to do is multiply this element by this and this element by this. So in this matrix also, you are able to see that this matrix scales all the x elements by an element factor of 3 and all the y elements by a factor of 5. And because it's 3 and 5, it's scaling them in different directions. So just imagine what's happening here. Here's your vector 3, 5. It's got 3 over here and 5 over here. So vectors over here, 3, 5. And just see what happens over here. Sorry, here's the vector 1, 2. Let's call this 1, 2. Okay. This one is not just extending this vector over here. This is not what's happening. It's extending it 3 times in the x direction. So when you have 1, it's taking it out to 3 times, and it's taking it 5 times in the y direction. So if you have 2, it's taking it 1, 2, 3, 4, 5. So it's taking it out here somewhere, like that. So it's moving it much more in the y direction than it is in the x direction. And therefore, its size is moving in a strange way because of the square root signs, and it's not easy to determine by looking at the matrix what will happen to the size change.